All right, okay. So my name is Rudy, and I'm going to talk to you about Speculate, and this is joint work with Colin Runciman, which is back there in the audience. Okay. Let's start really unusually. Let's start with related work. And I don't know if you guys know, but there's a tool called ItsBack. And okay, working. So ItsBack, you give it a bunch of Haskell functions. It does some testing and a bit of reasoning, and it prints out an equational specification. And for example, if you give it ID abs plus 0 and 1, it will print out this bunch of equations here. I mean, if you've seen it work for the last half an hour, you get the point. So ID of x equals x, abs is idempotent, plus is commutative and associative, and etc. What about Speculate? You give it a bunch of Haskell functions. Speculate performs some testing and reasoning, and it prints out an equational specification. But in addition to that, it's able to produce inequalities and conditional equations. You may note that ItsBack actually is able to produce conditional equations, but we actually started working in parallel in this stuff. So there's kind of different ways of doing the same thing. So there's kind of a separate contribution. But let's go to an example of Speculate so you guys can see what it can do. So if you give it ID abs plus 0 and 1, you get equations like you would get with ItsBack. But in addition to that, you get inequalities. Like, for example, x is less than or equal to abs of x. Abs of x is non-negative. Plus 1 is monotonic increases, and etc. And you also get conditional equations, like those. So there are a few rules for elimination of abs under certain conditions. And also the second one is quite interesting. So it says that for all non-positives, x plus abs of x equals 0. Okay. So why do we want to discover properties? Well, we can use those properties that we discover for understanding. Suppose we don't load a Haskell library and it doesn't have supposing it doesn't have documentation, and you have all these functions, these bits and pieces, and you don't seem to know how they fit together. You can use Speculate to figure out, have an idea of how they kind of go together. You can use them for documentation. Like you can bootstrap your documentation. You just run it, take the output and place it in your Haddock documentation. And I mean, you need to maybe clarify that a bit more, but that can be a start. You can use it for regression testing. So you take the properties that you get and you place them in a file, in a quick check style test file. And whenever you do a breaking change that breaks the properties, you are notified and you can go and fix it. You can use it for validation. You take those, you look at the properties you get, and if you get a strange law that is not, I wasn't expecting that. So maybe there's a bug with your code that causes that to appear. Or in other case, sometimes you get a strange law, but it's just that your interface is not organized in a nice way. Maybe that function A can be split into 2, and function B can have the argument swapped for nicer laws and so on. Okay. Now that we went through that, why do we want to discover properties? Let's see a couple of example applications of Speculate. Let's start with, let's try to reverse engineer insertion sort, from given an implementation of both functions. So if you pass sort and insert to Speculate with a few functions in the background, we get those laws. A few equations, some inequalities, and some conditional equations. And among the laws, we see those two laws, which are quite interesting. These are the base case of sort and the recursive case of insertion sort. So I was able to figure out kind of an implementation of insertion sort. And it also prints out the base case of insert among the laws and the two recursive cases of insert. So it figured out an implementation of insertion sort down to the insertion function based on the black box functions that we passed to Speculate. And we can just reformat it to get like kind of a like quite okay. Now let's see a second example. Let's try to let's go a little bit bigger and more complex. Let's try to discover properties about directed graphs. So we have this directed graph data type, never mind the actual representation, but it has like constructors, like empty digraph. We can add nodes, we can add edges. We can query for whether there are edges, nodes, and paths. And we can also query for lists of predecessors and successors of nodes. And we can also restrict the digraph, like find a subgraph. And what does Speculate say about those functions? It prints out those equations, and it prints out those inequalities and conditional equations. All in about 7 seconds. So it's somewhat quick. Let's take a look at some of them. Those are two interesting equations that I found. I selected them like somewhat arbitrarily. And so if x is an element of the predecessors of y, then y is an element of the successors of x. If an edge is in the graph, then element x, predecessors of y in the graph is true as well. We get that subgraph and add node, subgraph x's and add node x are idempotent. And we get that subgraph x's, it's like subgraph is commutative and add node is commutative. Of course, like when you, according to the parameters. We also get inequalities, like those you see here. The empty graph is less than any graph. Adding a node increases the size of the graph. Subgraph is less, and like adding an edge also increases the size of the graph. Can you guess how less than or equal to was defined for those graphs without looking at the source and just looking at the laws? Can anyone tell? Yeah, it's an order instance, but I meant like how like less than or equal, is it like lexicographic, or it's based on almost that. So it's actually based on subset relation between the sets of nodes and edges. So a graph is less than another if it's a subgraph. That's how it was defined. You can kind of see it from the law. We also have get conditional equations between digraphs. So like subgraph takes a list of nodes that we want to restrict the graph on, and this kind of tells us about its behavior. So if x is an element of x's, then applying subgraph after adding the node x doesn't affect the graph. Also, the second one, if x is an element of x's, actually add node and subgraph commute. Of course, add node x and subgraph x's commute. And we also get that one, if an edge is in the graph, if we try to add it, it's a no op. So, same as nothing. On the paper, we have a few more examples, like simplest functions, binary search trees, and one quite cool example is the regular expressions. We try to reach we try to find a full axiomatization of regular expressions, and we are almost able to do it, but we're short of one law. That's kind of future work. By the way, there are copies of the paper if you guys want to have them, and come talk to me after the talk, or they are around at the front. On the GitHub repo, there are even more examples, like there's microoperators, colors, and so on and so forth. Let's look at the runtimes. So the plus and abs example I showed you takes 2 seconds to run. The sorted insert takes 1 second, and directed graphs takes 7 seconds. For most other examples in section 5 of the paper, it takes a few seconds to a couple minutes to run. And details are in the paper of the benchmarks, etc. How does Speculate work? Well, in a few words, it's by enumerating, then testing expressions, using a bit of reasoning. So up to now, we have seen Speculate as a black box. The user gives it constants and functions, and Speculate spits out equations, inequalities, and conditional equations. But let's try to open the black box and see what's inside. There's quite a lot of stuff, but let's try to go through a few of them. So we take the constants and functions, we enumerate, we pass them to an expression enumerator, which enumerates expressions. Then those expressions are passed into an equation speculator, which will use the expression tester, in this case LinCheck, to figure out equivalence classes of expressions. It will also produce an equational theory, which will be fed back into the expression enumerator so that you don't enumerate redundant expressions and avoid sum of testing. And finally, we'll produce equations. Those, the byproduct of discovering equations is used to discover inequalities and also implications as well. But I'll show you a bit of detail of the equation speculator, and then I'll go into more details about the inequality speculator and the conditional equation speculator. Those are kind of the contribution of the thing. So, discovering equations. Do that by testing and equational reasoning, by using Knuth-Benedict's completion, and to produce equivalence classes of expressions, an equational theory, and equations. And no further details will be given here because this was kind of already existed when I started to work with QuickSpec. Kind of Speculate's kind of a re-implementation, and you can see the paper for how it's that done in detail, and either Speculate paper or the two papers on QuickSpec. So they differ a bit, but the point is, this is the initial example 0, 1 ID apps and plus. These are the equivalence classes you get and the equational theory. And I'm just emphasizing this because those are the things that are used in next steps in the steps of discovering inequalities and conditional equations. So how do you discover inequalities? It's based on two observations, and the first one is the number of equivalence classes of expressions is relatively small when you generate those equivalence classes. So here's an example, like for that initial example, like if you look at the last line, you see that with 7 symbols, you can create expressions, type correct expressions, about 7,000 of them. But there are only 30 semantically different actual expressions, so the number is not that big. The same thing when you allow up to 2 variables, like it's 144 times less than the possible number. Same thing with 3 variables. And the observation 2 is we already have all equivalence classes, and their smallest and simplest representatives as a byproduct of discovering equations. So to discover inequalities, what do? We list all pairs of class representatives. It's quadratic on the number of equivalence classes. And we test to select pairs that are less than or equal to. And those are the inequalities we discover up to size 3. However, there's a problem with those. Can anyone tell the problem with those inequalities that are shown here? Yes, so that they are redundant. That there is redundancy. So second or third, then redundancy. That's the problem. And that's even more of a problem when you increase the size to 4. Like you get this bunch of things, and there's even more redundancy, and it's not useful as this. We don't want to overwhelm the user with information. We need to fix this. So let's revisit the algorithm. We list all pairs of class representatives. We test to select pairs that are less than or equal. Then we discard redundant inequalities. But how do we do that? Well, there are a few rules. We discard instances, like we discard 0 is less than or equal to abs of 0 because that's implied by x is less than or equal than abs of x. We discard consequences of transitivity. And we discard something that I'm calling equivalent instances. But for that, you have to see the paper. And those are the discovered inequalities up to size 4, right? As you've seen before. And this is far less than the thing I showed here. This is a lot. And after the filtering, that's what we get. OK, that's how do we discover inequalities. What about discovering conditional equations? Well, if I write that equation up there, you might tell me that there's something wrong with it. What's wrong with it? Yeah, it's not true in general, and I mean, it's not true in general, but however, we can ask the question, when the above equation is true, when is it true? When is the above equation true? And it's true for all non-positives. So we kind of can, like, if it's true for all non-positives, then we write x is less than or equal to 0, implies x plus abs of x equals 0. That's an inequality over Booleans. The implication is an inequality over Booleans, and that's a good point that will be there in a few slides. So to discover conditional equations, we do what we just did. For each possible equation between class representatives, like we have like class representatives which we know that they are different, at least like they're not equal in general, but we try to explain if and when that equation holds. And one thing I would like to point out is that the weaker the condition, the better, because we want to cover more of the space of values that the property describes. So the top one is better than the bottom one. And so we find the algorithm. So for each possible equation between class representatives, we find the weakest condition from Boolean class representatives under which that equation holds. So we also use the Boolean class representatives as conditions. So it's kind of using it to build equations and conditions. And I mean, I won't have time to go to all details here. You can see more on the paper. There you will learn how to avoid testing all Boolean class representatives. We actually don't do that. And the hint is what was mentioned a moment ago, that implies is just less than or equal to for Booleans. And how we filter redundant conditions, because that's also an issue that we need to solve. And the resulting conditional equations are those that you've seen before, and after running the algorithm, you get that. So, in summary, Speculate, given Haskell functions, is able to discover equations, inequalities, and conditional equations. Properties that it discovers can contribute to program understanding and documentation, regression testing and validation, and also design refinement. And is shown effective in small case studies. And you can try it. You just install Speculate or go to the GitHub page and load it and run it. I've added a few. I want to say a few more things. Actually, I was watching talks this week, and I saw some talks where like people defined libraries that do all sorts of stuff, and I decided, I'll try Speculate on a few of them. So. First, Braquehais presented a pretty printer on Monday afternoon, 4 days ago, and I made a Speculate program that passes the functions he defines to Speculate, and it prints out a bunch of equations and inequalities about it. Here, inequalities defined as prefix, because I thought that was maybe we get nice laws out of it. Braquehais mentions the HugeSPJ pretty printer, and here is the program that I use it to pass the functions from HugeSPJ library to Speculate, and here are the laws it produces. Lastly, this morning, Andrei Markov presented his algebraic graphs library, and this is the program that I use to pass it to Speculate. I'm passing like the plus and times operator that he defines. This defines graphs as num instances, so you can like take products and sums. And those are the laws Speculate prints. And what's interesting is that some of those laws are actually in the Haddock documentation of the algebraic graphs library. So, I mean, this shows that like Speculate or even quick spec matter can be used to like help you reason about the things you write. Like you write something, and maybe what laws does this library have? So you pass it to Speculate, and you get those sorts of things. Yeah, and again, you can try it. And since I have a bit of time, I'll do a quick demo of it. So here is plus ID abs and the constants 0, 1, less than or equal, and less than. And I just do like make it. Yes, I use make files. And run. Yeah, we get a bunch of laws, and those are the things I showed you. There are some other stuff there, but these are the equations, the inequalities, because implication is just an inequality over booleans, and the implications. And I mean, there are like other examples here. So I guess, let me see here. So tuples, zip. So I just want to see add any function to the signature so that we can see what it prints. Yeah, let's do that. So constant times that, and do make g plus abs, g plus abs. There you go. So thinking a bit. So those are the equations. So we do get commutativity of both plus and times, and you get that abs of x times abs of x is just xx. So I mean, someone had the idea of like using those as rewrite rules to simplify programs. That could be a good candidate. Simplifying, like avoiding applying abs, and those can be easy. I had the idea of using those as like hlint rules. So you place them in like an hlint file, and you get like suggestions for improving the code. And let's see the implications. So we get those, and also distributivity is on a further size, but yeah, we can try to make it do that. So I just set the size limit to, let's say, I think 7. We'll get it. Is it 7? Yeah, 7. It's thinking a bit more, so let's move. While it thinks, I'll move it up so you can see the inequalities there. Thinking. Hmm? Oh.
One we were showing us examples that works very well. What are typical examples where the tool doesn't work as well as it would? What are the
I mean, if you add too many if you add too many functions in the signature, like simply the space of terms we have to search kind of is too big, and it's not able to cope with it. So we have to if you have a big library, maybe you have you want to use Speculate first in the core, and then some other functions around it, and things like that, like to deal with it. So the more functions you have, and the bigger the size of the terms you are exploring, the longer it takes. So it's taking too long. Maybe I'll cancel it and maybe remove some stuff so we get it faster, maybe.
What about higher order functions and lambda terms?
Oh, it does. It's able to deal with higher order functions. Oh, there you go. That's distributivity there. So at lambda terms, like Speculate is not able to deal with lambda terms, and higher order functions it does deal with it. So let me open the insert sort example. So let me add here constant. Let's see. Not add. It's all, and the second argument must be. It's kind of a funky DSL I have for binding types. Make g insert sort 0 dot test. Ooh. What's wrong here? So all. What's the type of all? Oh yeah, it's a list of int. So I mean, this is a cool precondition there. So if x is less than or equal to all element of vectors, you get those resulting facts about it. So yeah, I guess I need to stop. So we can just go install Speculate, and thank you for listening.
Okay, now I might put it on stage if I know. That's it, yeah, I guess we have time for a few questions.
So, for these equivalence classes and also for the comparison, so it's fine if there's just one type involved, like int or set. But libraries often are manipulating, some int, some sets of sets, so that you need to define many order operations. And there might be equivalence classes with different types. Do you handle all of that?
So that's one of the differences of Speculate and QuickSpec. So let me go to so I had a slide for it. It's quite small, but you can kind of see it. So QuickSpec can deal with polymorphic functions. So you actually, you just need to supply a polymorphic function once. But in the case of Speculate, it's only monomorphic. It's kind of a simplified.
I was just talking about libraries whose inputs and outputs were more than one type of involved.
Oh no, it can deal with it. Like I mean.
More than one ordering, more than one.
Oh yeah, it can do that. Yeah. I mean, in the examples I've kind of shown you. Let me see. So here, for example, we have two orderings here. So implication is just less than or equal for booleans. So there you go. But there are two orderings there, and it prints laws about those. So it prints laws about all types it can find. So it kind of looks at the types that are provided in the signature, and yeah, that has worked.
Can you find things about when functions fail with the added derivatives that only work if you're not dividing by zero?
No, I haven't. I don't think the current version of Speculate deals with like bottom values and defined values, so it doesn't like find laws about that specifically. But that I think that's one thing that's in my to-do list for Speculate. Like getting, if you apply this function this way, you get an error. Like you get like undefined or something. But that's a good question and comment. Yeah, so I'm thinking. I think it could be able to do it, but nan has a special thing because nan is not equal to nan, so it may cause some trouble with that. So because doubles and floats are the only like types in Haskell that are not reflexive, and it's like it kind of maybe can cause trouble. But I haven't tried it. Maybe I'll try it and see what it prints out.
So you mentioned having to do some work to avoid redundant equations and inequalities. Are there sorts of equations and inequalities or sorts of redundancies that you can still handle?
Yes. So the one example is in the first slide. So right at the start, I showed you those four conditional equations. The last two ones are just rewritings of one another. Like they're just the same thing. You just use commutativity in plus here and alpha rename them, alpha rename x and y. And I just haven't got to it. And like because the way I created those rules for removing redundant laws were kind of ad hoc. So I kind of saw, this is redundant. I'll create a law for it, and so it was that was the process I've used. So this is one case where I didn't work on it, but plan to work on it in the future. Okay, thanks for the question.
Yeah, sure. So maybe continuing off Simon's question. So you checked out Bernardi's printing and could Speculate be used to discover whether two libraries are equivalent and when they are not?
it kind of could in the sense that you can provide both libraries to speculate and then compare the laws you get, and if the laws are the same, maybe they're equivalent. But I would, to do that, I would maybe use that in conjunction with a property-based testing tool and actually test laws and like try to use a law to compare all functions, and that could be a way to do it. Does that answer the question? Is that not exactly what? Yeah. Okay. Yeah, that thought crossed my mind, but I haven't had time to go through with it. But that's one thing that's in the back of my head, like using those to like improve code. Like for example, when I mentioned HLint, which is like a tool that suggests like cleanups for the Haskell code, and it only usually it works for the standard functions because it knows how to deal with them, but not for user-defined libraries. So like Speculate could find simplifications in user-defined libraries. But I mean, we have to be careful not to make it like when simplifying, making it slower. So, but yeah. That could certainly be used. And one detail though, QuickSpec uses random testing to generate those. Speculate actually uses enumerative testing with link check. So the test cases here are enumerated. So yeah, that's another difference since you.
Right. Thanks.